For generations, both scientists and those captivated by the stars have turned their attention to Proxima Centauri, the star nearest to our own, wondering what mysteries it may conceal. Located just over 4 light-years from us within the Alpha Centauri system, Proxima Centauri is known to have at least one planet, Proxima B, often viewed as one of the most likely candidates for supporting life beyond Earth. Proxima B has remained elusive until now. The James Webb Space Telescope, JWST, is the most sophisticated space observatory developed by humanity, has produced the most detailed image ever captured of Proxima B. This achievement marks a major advancement in how we comprehend distant planetary systems. The photograph was nothing short of astonishing. At first glance, it appeared as expected, a lone sphere floating in the darkness of space. But what set this image apart wasn't just its sharpness, it was the closeness it conveyed. For the first time, scientists could discern atmospheric layers, temperature variations, and even potential surface formations on a rocky world orbiting a distant sun, thanks to JWST's cutting-edge optics and infrared capabilities. Researchers now have an unprecedented view into a planet long held as a symbol of possibility. Proxima B lies within the habitable zone of its host star, meaning conditions might allow liquid water to exist. Until this image, most of what we knew came from indirect observations, estimates of mass, orbit, and distance. Instruments like Hubble and powerful ground-based telescopes could only provide data through radial velocity changes, spectral shifts, and probability models. No observatory had ever produced a direct image of Proxima B with such clarity till JWST. What enables JWST to make such a groundbreaking observation is its ability to detect infrared light, allowing it to see through space dust and pick up faint signals from faraway celestial bodies. Positioned at the second Lagrange point L2, it orbits the Sun in alignment with Earth, safely distanced from the atmospheric interference of our planet. Its gold-coated mirrors, nearly 7 meters in diameter, collect light with unmatched precision. When directed at Proxima B, JWST provided something that astronomers had dreamed about for decades: a visual representation of the planet, star, and the space surrounding it. The planet appears slightly larger than Earth, and its visible landscape suggests it may have geological features like mountains or vast ridges. Surface temperature differences point to the presence of weather systems, perhaps even clouds. Most significantly, the telescope's sensors picked up telltale infrared absorption lines hinting at atmospheric gases such as carbon dioxide, water, vapor, and a faint signature yet to be conclusively identified. This level of clarity represents a turning point in exoplanetary research. Astronomers are no longer limited to indirect detection methods. They can now study the reflected and emitted light of a planet's surface and atmosphere directly. This shift transforms theoretical speculation into tangible exploration. Proxima B is no longer just a concept in models or equations, it's a real world with observable features. What's remarkable is how this new data challenges earlier theories about Proxima B's environment. Previous models, constrained by limited information, imagined a planet locked in place by gravity, scorched on one side and frozen on the other, stripped of its atmosphere by violent solar flares from its red dwarf star. But the image tells a different story. Thermal readings across its surface show a more even heat distribution, implying that an atmosphere might be present, circulating warmth around the planet. This opens possibilities for climate regulation, cloud cycles, and most compellingly the potential for life-supporting conditions. The implications stretch far beyond Proxima B. This image is a clear indication of what JWST can accomplish. In the study of other planets, Proxima B has long been viewed as a leading candidate for habitability because of its location and size. Countless other exoplanets await the same level of examination. Some are even more similar to Earth or orbit calmer stars. JWST's achievement here hints at a future where detailed imaging of many exoplanets becomes routine. There's something quietly profound in this moment. From our tiny place in the cosmos, humanity has managed to peer outward and clearly observe a world that may be like ours. This isn't just a technical success, it's a moment that captures the essence of human curiosity. It's a glimpse into what might be possible. For seasoned astronomers, this is a moment of long-awaited reward. For newcomers, it's a compelling reason to explore further. The level of technological precision involved is astounding. Keeping a fixed gaze on a target for light years away, isolating planetary features from the glow of a nearby star, and decoding faint infrared signals all required an extraordinary marriage of hardware, software, and international collaboration. This success isn't just about tools. It's about decades of collective effort, shared goals, and relentless ambition. There's also a deeper, more philosophical undercurrent to this discovery. The ability to see Proxima B in such detail signals a shift. Exoplanets are no longer distant ideas, they are places. You might have skies, weather, terrain, maybe even conditions that foster life. This realization changes how we perceive the universe, not as a void, but as a realm filled with rich, dynamic environments. The scientific community has reacted with intense excitement. Researchers are diving into the data to refine their models of planetary formation, atmospheric composition, and orbital mechanics. Spectral findings hint at complex chemical processes in the planet's atmosphere, possibly influenced by the unpredictable flares of its host star. Some research teams are assessing how these processes might affect any signs of life. Others are exploring how this new image could shape future missions, including probes powered by light sails or other advanced propulsion concepts. One of the most debated topics is habitability. If Proxima B retains a stable atmosphere and has moderate surface temperatures, it meets the basic criteria for potentially supporting life. But habitability involves more than just temperature, involves the possibility for ecosystems to arise, for chemistry to grow in complexity. As the image sharpens, the conversation evolves from "could life exist?" to "what might that life be like?" There's also growing interest in comparing Proxima B with planets in and beyond our solar system. Its similarities to Earth, Mars, or Venus could help scientists refine their theories of planetary development. Did it experience a runaway greenhouse effect like Venus? Is it in a similar state to early Earth? Does it still have active tectonics? These are no longer abstract speculations. The clear images and rich spectra, they become questions we can now test. Surface details hint at varied terrain. Differences in reflectivity known as albedo suggest a mix of surfaces, while some regions reflect more infrared light, which may mean icy or mineral-rich deposits. Others absorb more, possibly due to darker volcanic rock. If this holds, it suggests that Proxima B is geologically active, which would be a major indicator of planetary vitality. Geology plays a critical role in shaping a planet's environment. On Earth, plate tectonics regulate the climate and maintain atmospheric balance. Volcanic activity releases gases vital for sustaining a dynamic atmosphere. If similar processes are active on Proxima B, it raises new questions about how planets across the galaxy evolve. There's also a possibility, though not yet confirmed, that water might exist. While JWST can't directly observe rivers or lakes, its findings suggest a stable atmosphere and a location in the habitable zone, making the presence of surface water plausible. If water has been there long enough, it strengthens the argument for life. Life remains the ultimate question. JWST isn't specifically designed to detect life, but it can identify chemical signatures, gases like methane or ozone that might indicate biological processes, though no definitive biosignatures have been confirmed yet. The detection of carbon-containing gases and water vapor makes Proxima B a top candidate for future study. With such a detailed image now available, the possibility of launching missions toward Proxima Centauri becomes more realistic. Engineers and physicists are rethinking the potential for sending miniature spacecraft propelled by light. Once seen as theoretical, this idea now has a specific destination. A probe traveling at 20% the speed of light could reach Proxima B in just over 20 years. Beyond science, the discovery has inspired a wave of creative responses. Educators, artists, and storytellers are revising how they depict alien worlds, now using a real example. No longer limited to imagination, they have a model a planet with texture, contrast, and atmosphere. This leap from speculation to visualization changes how we learn, teach, and dream. Students won't just read about Proxima B, they'll see it as a place, although many aspects still require confirmation and further analysis. One thing is unmistakable. This image is the start of a new era. It's the beginning of a chapter where direct observation replaces conjecture. As JWST continues to operate and future tools expand our capabilities, this moment will remain a milestone, the first time a distant planet moved from theory to vivid reality.